Hello there, Mr. Sutton here, bringing you the AB Calculus 614 Extra Practice Number 3 solutions on volumes of known cross-sections. For this no calculator free response problem, we have this R region in the first quadrant enclosed by f of x equals square root of cosine of x, and g of x equals e to the x, and also this vertical line of x equals pi over 2. So this is all shown in the figure below. So it helps to keep in mind that, let's see here, g of x, e to the x, that's probably the easiest one to pick out. That's this function that starts at 1 and is going up. And then this radical cosine of x is going down here. And here's our vertical line they were talking about. So given this setup, our first task is to write but not evaluate an integral giving the area of R. So in general, you're going to have the integral from left to right of top minus bottom. So in this case, that's going to be the integral from 0 to this line of pi over 2. So those are our limits of integration. And top minus bottom in this case, since we just said that g of x is this function up here, and f of x is this function down here, we want to do g of x minus f of x. And that's going to give us those distance strips that we can then add up to get the area. So I'll write g of x minus f of x dx, and they said not to evaluate it, so I'm going to take them at their word and call it done. For this part of the problem, they want us to find the volume of the solid generated when R is revolved around the x-axis. Unfortunately, this is not one of those set up but do not evaluate ones. We have to take it out all the way. So let's start with figuring out, first off, limits of integration. It's going to be the same as the area. We're going from 0 to pi over 2. And then for the actual formula for the volume, we need to know what the cross-section is going to be. Since this is a solid of revolution, we know that we're dealing with either disks or washers. Taking a look at this area, if we're going around the x-axis, then there is a gap between the bounded region and the axis of revolution. That gap in there tells me I'm going to have to use donuts or washers as my cross-section. So I'm going to start with a of x equals pi times big R squared minus little r squared. The big radius, that's the distance from the axis of revolution to the further away function. So that's actually just the e to the x there is our big R. And then little r is that closer function, the distance between that and the axis of revolution. So that just ends up being radical cosine of x that I'm squaring and subtracting inside there. So now my volume is just going to be the integral from 0 to pi over 2 of, well, all of this. Okay, so I'm going to simplify things a little bit before I actually put it in the integrand. So I have a pi, and in a parentheses, I'm going to write this as e to the 2x minus, and then this is just going to be cosine of x, and we have a dx hanging around out there. So now taking my antiderivatives, I'm actually going to pull pi outside of everything. And antiderivative of e to the 2x, that's going to be e to the 2x divided by a tail of 2, so 1/2 e to the 2x. So we have a pi outside, we have a 1/2 e to the 2x, and then minus cosine of x antiderivative, that's going to be minus sine of x. And all of that being evaluated from 0 to pi over 2. So I'm going to have a pi, and now inside I'm going to have all this stuff with pi over 2 plugged in. So I can actually rewrite this as just e to the pi, because the 2's are going to cancel. And then this is minus sine of pi over 2. And we're going to subtract now all of this stuff with 0 plugged in. So this is going to be 1/2 e to the 0 minus sine of 0. Since I've got all constants here, I could actually just stop and be done. But if I want to make my life tougher, I can keep simplifying. So let's see here. Can't do much with 1/2 e to the pi, but sine of pi over 2, that's really 1. And this is going to be, let's see here, minus 1/2, because e to the 0 is just 1. And sine of 0 is 0, so that doesn't make any difference. So we have pi times 1/2 e to the pi minus 1 minus 1/2. And if I really want to keep on going, I could write this as pi over 2 e to the pi minus 3/2 pi, or 3 pi over 2. And I could even put this all in one big fraction if I wanted, but I think I'm just going to quit while I'm ahead here. For this last part of the problem, they're telling us that region R is the base of a solid whose cross-sections perpendicular to the x-axis are semicircles with diameters on the xy plane. All right, we wanted to write but not evaluate an integral that gives the volume of this solid. So my area formula in general for these cross-section areas, that's going to be, I'm going to call this A2. This is going to be A sub 2 of x equals, let's see, 1/2 pi r squared, because we're dealing with semicircles. And if you're wondering why I wrote A2 here, that's because on the last problem I did, I defined A sub 1 as something else. It was the washers I was using for my solid of revolution. But anyway, we're here now. Let's keep going. So for the radius, to define that, well, they said that the diameter of these semicircles that are popping out of this area basically are on the xy plane. So the distance between the two functions, e to the x minus radical cosine of x, or I guess you could say g of x minus f of x, that distance between the functions is the diameter of these semicircles. The trouble is, this formula right here doesn't take diameters, it takes the radius. So I need to replace r with g of x minus f of x over 2. So taking half of that distance between the two functions, that's going to give me the radius that I need for this formula. So now this whole thing is my a sub 2 of x. I'm just going to integrate this, like everything else, from 0 to pi over 2. So I'll just write that my volume equals 0 to pi over 2 integral of a sub 2 of x dx. And since I've defined this a2 up here, and everything up here is defined in terms of x, I am done. For this calculator-based free response problem, we are given this R shaded region in the first quadrant between e to the negative x squared and 1 minus cosine of x. And our first task here is to find the area of this R region. So I'm going to make my life a little bit easier here by defining these functions as f of x for the e to the negative x squared and g of x for the 1 minus cosine of x. That way I don't have to keep rewriting them. Next, in order to find the area here, my basic setup is I have an integral from left to right of top function minus bottom function. But first I need to figure out the right side here. I know the left x value is going to be 0, but I need to find out where these functions intersect to get the right limit of integration. So let me set f of x and g of x equal to each other and basically find that intersection on my graphing calculator. So here I am in my y equals. I'm storing f of x, that e to the negative x squared one is y1, and g of x is going to be y2. So let me graph these on the interval from, let's see here, I think 0 to 1.5 ought to do it. Probably could even get away with 1, but let's do 0 to 1.5. So let me zoom fit now that I've got those x min and x maxes set. So there's f of x. Here is g of x. And I just need to see what this point of intersection is. It looks pretty close to 1, but that's not going to be close enough for my purposes. Let me do second trace, intersect, option 5, and we'll just move my spider closer and press enter 1, 2, 3 times to get the exact value. That's going to be 0.9419 or 942, however far you want to round that. It doesn't really matter because I'm actually going to store that as a value. I'm going to call that k forever after. So whenever I say k, you think this number here. And on my calculator, I'm also going to store that. So let me quit out of that screen. And I'm going to go to the stow button. And I'm going to store the x value I just found as alpha k. So let's see, where's k? Right here. All right. So now that I've got that, to get this area here, I just need the integral from 0 to k of, we said top minus bottom, so that's going to be f of x minus g of x with a dx out there, and now I can just do that on my calculator. So back on my calculator, I'm going to do math 9, so integral from 0 to k, so alpha, let's see, alpha k, there we go, well, that's alpha q. Let me try alpha k, there we are, alpha k. And then I need to do f of x minus g of x. So that's going to be alpha trace y1, because that's where I stored f of x, minus alpha trace y2. That'll give me g of x. Put an x next to the d there, press enter, and our area is about 0.591 if I round that off. For this part of the problem, I want to find the volume of the solid generated when r is revolved around the x-axis. So my limits of integration for the integral I'm about to do are going to be the same as before, 0 to the k value I defined back in part A. But now, for the thing I'm integrating, I need an area formula, the area of my cross-sections. Since this is a solid of revolution, I know that I'm choosing between disks and washers. And to figure out which one, I see here that I have a gap between my shaded region and the axis of revolution, which is the x-axis in this case. Because I have this space in here, that tells me that I need washers, basically donuts, for the cross-section shape, because they have that hole in the middle, which this space is giving me. So I'm going to use a of x equals pi times big R squared minus little r squared. And I'm actually going to write a sub 1 of x equals all this stuff, just because I kind of looked ahead and I know that I'm going to be making another cross-section area formula in part C, so I don't want to confuse it with this one. So anyway, big R, that's going to be the distance between my axis of revolution, the x-axis, and the further away part of the bounded region, which is the f function up here. So I'm going to have pi times, this is going to be f of x squared, and for the little radius, that's going to be the distance between the x-axis, the axis of revolution here, and the closer function, which happens to be the g function. So we're going to be doing minus g of x squared. And let me do the integral now from 0 to k of basically just this a sub 1 of x function, dx. And I'll do all that on the calculator. So to put this into the calculator, let me do math 9. And I've still got my limits from 0 to k, so alpha k. This time around, I've got a pi in there, and I didn't have to put the pi inside, but I'm going to. And I've got a parentheses here, and in here I basically need big R squared minus little r squared. So in this case, the f function, that was y1, so I'm going to do alpha trace y1, and I'm just going to square that, minus, now I need y2 squared, because that's where I stored the g function. So alpha trace y2, square that. Don't forget to close your parentheses that you opened, because you're distributing that pi in there. And then let me put a dx over there, press enter, and that's about 1.747 if I round that off. For this last problem, they're telling me this region is the base of a solid, and for the solid, each cross-section perpendicular to the x-axis is a square. So find the volume. So basically, we have these squares coming out three-dimensionally from this shaded region, and we need to find the volume of the shape that comes out of that. So we're still just integrating an area across a certain interval. We just have a different cross-section for the area. It's not a disk or a washer, it's a square. So let me get the area of a square. I'm going to call this a sub 2 of x equals s squared. That's just the general formula for a square. And I'm writing a sub 2 because I already used up a sub 1 for my washer back in part B. So now this square, the side of the square, is just the distance between these two functions. So I can write this as f of x minus g of x squared. And now I'm just going to integrate this thing from 0 to k, just like everything else I've done on this problem, just using the limits of integration for my bounded region that I found back in part A. So I'll just write a sub 2 of x dx in there, and the rest of this is up to the calculator. So here's what this looks like on my calculator. I still have math 9, integral from 0 to alpha k. This time I'm doing y1 minus y2, because that's where I stored my f and my g functions. And I'm inside a squared parentheses for those. I've got my dx, press enter, and that's about 0.461 for that final answer.